Two important characteristics of a buffer are its buffer capacity and its pH. Buffer capacity depends on the amount of acid and conjugate base present in the solution. Typically, a buffer can work within plus or minus 1 pH units. Okay, so if I had a buffer of 6, I should expect that buffering system to work between pH 5 and 7. Okay. Once I get out that range, get below that 5 or that 7 for that particular buffer pH 6, then I expect that buffer capacity not to be as good. Okay, it's going to be changing dramatically in pH units as I add more acid or base. It's only a certain range where it can absorb that additional acid or base and keep that pH relatively constant. Okay. The other issue involved is the dilution factor. As my conjugate acid-base dilution gets more and more diluted, that buffer capacity is also going to break down. Okay, so the concentrations have to be similar, and they cannot be very diluted. If it gets too diluted, then that buffer capacity will also break down as well. Next topic illustrates how to calculate the pH of a buffer by a special equation, which is referred to as the Henderson-Hasselbalch Equation. But I personally suggest you follow it the same way we just did it just a few minutes ago on the previous homework set, where we basically said you take the soluble salt, you break it up, then you take the acid hydrolysis, do your ice table, and calculate it. Okay, work it that way, you can get to the correct answer. You're free to use the Henderson-Hasselbalch equation, but you gotta realize it's only for buffers, and you gotta use it correctly. Okay, I suggest as you learn in pH calculations to follow a systematic approach, which is what I'm trying to show you. That way you can look at all these problems look exactly the same. That way you won't run into these careless errors. Now the Henderson-Hasselbalch equation is very important to organic chemists and biochemists because that's the way they tend to do their calculations, by plugging it into this equation. As I said, I'll show you this because if you move on to other chemistries, you may run into this equation, but I also suggest at this time to follow the systematic approach that we've been following in this process. So how do you calculate, how do you prepare a buffer for a given pH? Okay. Well, a buffer must be prepared from selecting a conjugate acid-base pair in which the Ka of the acid is approximately equal to the desired hydronium ion concentration. So if I want a certain pH that's related to hydronium, right? So I get my hydronium concentration, then take that value, look into tables, and look for a Ka that's similar to that concentration. So I'll figure out my concentration of hydronium from the pH, then look in tables for the Ka that's similar to that. Now, it may not be exactly that, but I can sway that by adding more acid or base to get it to the correct value I'm looking for. Okay. Now, your organic and biochemists don't happen to do it this way. They're going to take the negative log of both sides, which is going to give me a pH is approximately pKa. They tend to have tables that have pKa values. Okay. So if I want a pH of 7, then I can go look in the pKa table for something at 7. Now, if it's not exactly what I need, then once again I can add conjugate acid base changes to change the raise or lower the pH. If I want something to be a little higher pH, say for instance, I'm looking for pH 5.5, and I look in the pKa tables and I find 5 pH, and that's close. Well, I'm going to need a pH a little high. I need it to be a little higher, so I add a little bit more base. If I add a little bit more base, then I can get a higher pH. Say I wanted something that's 4.5 and I'm using a pKa of 5. Then I add a little bit less base, meaning more acid. That way I get a lower pH, okay, until I get the exact pH I want. So I take the components between my conjugate acid base, I sway that to get to the actual pH I'm looking for. If I want that pH to be exactly that pKa, well, then I would use the same concentration of acid and base. That way it cancels itself out, and I'll show you that in the equation later on. So let's consider a weak acid, okay, hydrolysis, which is HA, gives me hydronium and A minus. I can write the Ka for this, which is hydronium ion times A minus divided by HA. Now, ultimate goal is the pH of a buffer at a certain pH. What is pH related to? Well, pH is related to hydronium ion. Okay, so let's rearrange this equation and solve for hydronium ion, which means I got hydronium ion is equal to Ka times a concentration of HA divided by A minus. Okay, now this is how I would tend to work these problems because I already know the pH I want, which gives me hydronium. I know the Ka, I selected some Ka. I can arbitrarily pick some concentration of my weak acid. I can calculate how much A minus I need to make this buffer pH or whatever I'm looking for. But organic and biochemistry are kind of like an equation, so I'll go ahead and derive the equation they use for you. So I'll take this same equation and I'm going to manipulate it to get to something called the Henderson-Hasselbalch equation. So I got my equation. I'm going to take the negative log of both sides, so I haven't changed anything. Okay, it's still equivalent because I took the negative log of both sides. Then I'll take this expression here, the KAHA over A minus. Mathematically, I can take the log of that number, or I can also subtract the two, being since I had that negative there, and rearrange it to the negative log of Ka plus the negative log of HA over A minus. Okay, that's equivalent. And then I go one more step. What's the negative log of hydronium? Well, the p of any function equals to the negative log of any function equals to the p of that function. So then I can change that negative log of H3O plus to pH and take the negative log of Ka and call that pKa, which gives me plus the log of A minus over the concentration of HA. Now notice these two components have flip-flopped. Mathematically, I can get rid of that negative sign by reversing my concentration. So now I got A minus in the numerator and HA in the denominator. This equation right here is referred to as your Henderson-Hasselbalch equation. This is an equation that you can use only for buffers though. Okay, this is for buffers. It doesn't work for any other situation, only for buffers. So there's one that you can use to calculate buffers, or you can follow this procedure that I showed you earlier. More generally, you can write this as pH is equal to pKa plus the log of the concentration of your base component divided by your concentration of your acid. Now, one thing I want you to keep in mind, it is the concentration of your base, the total concentration. Say I had a concentration of 0.1 molarity of calcium acetate. Okay, and I'm trying to plug in my acetate concentration. Okay, my acetate concentration into this formula. It's 0.1 molarity of acetic acid, okay, of calcium acetate rather. Okay, for every one calcium acetate, how many acetates do I have? You have 2. So in other words, if I may have 0.1 molarity calcium acetate, but I have 0.2 molarity of acetate ions. And that's the value I'm plugging in here. Okay, you need to keep that in mind when you use this equation. We could take this equation and I could do the same problem we did earlier. Remember the previous example, we said an aqueous solution of 0.2 molarity of formic acid and 0.18 molarity of sodium formate had a pH of 3.63. We calculated that when we said the soluble salt first, we did the acid, did the ice table, we did a whole calculation, and we came up with 3.63. We can do the same calculation with this Henderson-Hasselbalch equation. Okay, so let's do that. pH is equal to the negative log of Ka. I changed that pKa to the negative log of Ka since we don't have pKa's in our tables for the freshman books. Plus the log of my concentration of my formate ion divided by my concentration of my formic acid. I've got to plug in my values. pH is equal to the negative log of 1.7 times 10 to the negative 4th is my Ka. My formate ion, we have 0.18 of sodium formate, which is a 1-to-1 ratio between sodium formate and formate. Therefore, I got 0.18 formate ions divided by my concentration of my acid, which is 0.25. So I take 0.18 divided by 0.25, take the log of that number, add that to my negative log of 1.7 times 10 to the negative 4th, and I get the answer of 3.63, which is the same answer we got the way we calculated previously. This equation relates the pH of a buffer, and remember it's a buffer, to the concentrations of the conjugate acid and bases. It is known as the Henderson-Hasselbalch equation. It's only used for buffers. Now you could work this problem just like we did in the past, just as I told you, soluble salt, hydrolysis, ice table, and that's the way I suggest you do it. Okay, but you can use the Henderson-Hasselbalch equation for buffer situations. Now, one thing I do want to show you with this Henderson-Hasselbalch equation is pH equal to pKa. Okay. If, say, for instance, I had 0.1 molarity of my base and 0.1 molarity of my acid, okay, well, what happens 0.1 divided by 0.1? That's equal to 1, right? What's the log of 1? The log of 1 is 0. Okay, so an instance where the concentration of my base and the concentration of my acid are equal, they're the same concentration, then pH equals pKa. So if I want my pH to equal that exact pKa, then I took my concentration of base and acid to be the same. Now, say I wanted my pH to be a little higher than that pKa value. Well, then I would have a little bit more base. Say I wanted that pH to be a little lower than that pKa. Then I add a little bit more acid compared to that base. That way I can get that pH to go down. So you sway, by swaying your concentration ratio here, you can sway that pH to go up or down depending on what you need for the buffer that you're looking for. All right, let's prepare a buffer, let's say a pH of 4.90. So to prepare a buffer of a given pH, for example, pH of 4.90, we need a conjugate acid-base pair with a pKa close to the desired pH. So I'm looking for a pKa was about 4.90. Now, as I mentioned, we don't have pKa tables in freshman books, so we're going to have to do it on the basis of hydronium ion. So I need to figure out what is the what concentration of hydronium for a pH of 4.90. Well, remember, hydronium ion is equal to 10 to the negative pH, which means the hydronium ion concentration I'm looking at is 10 to the minus 4.90, which is 1.3 times 10 to the negative fifth. So I'm looking for a Ka that's very close to that hydronium ion concentration. Okay, hydronium ion concentration associated to a pH of 4.90 is 1.3 times 10 to the negative fifth. So I'm looking for a Ka that's very close to that to start my buffer system. Okay. Here's some suggestions. We have acetic acid, which has a Ka of 1.8 times 10 to the negative fifth. We have carbonic acid, which has a Ka of 4.3 times 10 to the negative 7. And I have nitrous acid that has a Ka of 4.5 times to the negative 4. Which one of these three components, these three acids, would you want to start your buffer system to make your buffer a pH of 4.90? Remember, I want something that's close to my 1.3 times 10 to the negative fifth. Which one of these three is the closest to that 1.3 times 10 to the negative fifth? Yes, the acetic acid. I have 1.8 times 10 to the negative fifth. That's the closest one, so that's the one I'm going to start with. So that's the one I would pick, and then I'll pick a salt to complement that acetic acid, most likely something like sodium acetate. Now, the Ka for acetic acid is 1.8 times 10 to the negative fifth, and its pH or pKa is 4.74. Okay, I got that by calculating using your hydronium ion concentration. If I have equal amounts of acid and base, my acetic acid and sodium acetate, then my pH will be 4.74. That's not what I want, though. I don't want 4.74. I want 4.90. Okay, so I need that pH to get a little higher. Okay, so how am I going to do that? Well, that would mean that I'm going to have to need a little bit more acid or a little bit more basic salt to get that pH up. I'm going to need more basic salt. So when I get finished, my concentration of my acid and base should not be equivalent. If I have them equivalent, I'll get a pH of 4.74 for the buffer. I want it to be a little higher. I want it to be 4.90. So I should have more salt, more basic salt, than I have acid as my components to get that pH. So you can get a buffer of pH 4.90 by increasing that ratio of base to acid, meaning more basic salt. Okay, so I want to make my buffer. I want a 4.90 buffer. I'm going to use, and I'm arbitrarily saying I'm going to use a concentration of 0.1 molarity of acetic acid. Now I got to figure out how much sodium acetate I need to make that buffer to be 4.90. I'm going to show you two different ways to work this. I'm going to show you the Henderson-Hasselbalch way, and I'm also going to show you my way, and you can decide which way you want to do. Okay? So, I know my concentration, I know my pH, I know my Ka, which will give me my pKa, so I can calculate for that one missing variable, which is my acetate ion. So I'll plug in have my Henderson-Hasselbalch equation. pH is equal to pKa plus the log of my concentration of my base divided by my concentration of my acid. Remember that pKa is equal to the negative log of my Ka. Okay, this being Ka, 1.8 times 10 to the negative fifth, which is 4.74. So I get 4.90 is equal to 4.74 plus the log of my concentration of my acetate divided by my 0.1, which is my concentration of my acid. Do some arithmetic. I bring my 4.74 over, which is 4.9 minus 4.74, which is equal to 0.16, which is equal to the log of my concentration of my acetate divided by my 0.1. I'm going to now get rid of this log by doing the anti-log, which means now it's 10 to the 0.16 equal to my concentration of my acetate divided by 0.1. Multiply both sides by 0.1, which means it's 10 to the 0.16 times 0.1 is equal to my concentration of acetate, which 10 to the 0.16 is 1.45 times 0.1, which is 0.14 molarity, which gives me my concentration of my acetate, which in this case is the same concentration of the sodium acetate I need. Now, one thing to keep in mind about this though is its mole to mole ratio. You got to realize we need 0.14 molarity of the acetate ions. Okay? Now what would happen if it wasn't using sodium acetate, but instead I was using calcium acetate as my salt? Okay, what would change? Well, you got to account for your moles, right? There's 2 moles of acetate ions for every 1 mole of calcium acetate. Okay, your moles cancel, which then means I get that I have 0.070 molarity of calcium acetate is needed. Okay, so it's something to keep in mind. It's mole to mole. Okay, in this particular case, I have a 1-to-1 between acetate and sodium acetate. I have a 1-to-2 ratio when I'm talking calcium acetate. Okay, so I'm going to need half as much to get the amount of acetate ions I need. That's just something to keep in mind when you're doing this. Now, for homework, when we do the calculations, we're going to go one step further than this and do some Gen Chem 1. I'm going to want you to calculate the mass of that calcium acetate or sodium acetate we need, because that's how we make solutions. I got a solid, I'll put it in a solution and make my solution. Okay, this is how I would do it with Henderson-Hasselbalch, but that's not how I would approach this problem. I would approach it the same way we're doing everything else, which is in a case where I say, okay, I'll write my equilibrium. I got my hydrolysis of my acetic acid, which gives me hydronium ions and acetate ions. If I set up my Ka, I know I got Ka is equal to hydronium ions times my acetate ions divided by my acetic acid. Same thing we've been doing. But in this case, I know my Ka, right? I know my acetic acid. I know my hydronium, not directly, but indirectly. Okay? So basically, I got one equation and one unknown. This is the only thing I don't know. So I'll just do this math. First, I'll figure out my hydronium ion concentration, which is 10 to the negative pH. Okay, negative pH. Which gets me 1.3 times 10 to the negative fifth molarity. Rearrange my above equation. So I rearrange this equation, solving for just my acetate ion, which means I have Ka times my concentration of my acetic acid divided by my hydronium ion. plug in my values. Which gets me 1.8 times 10 to the negative fifth for my Ka, times my 0.1 for my acetic acid concentration, divided by my hydronium ion concentration, which is 1.3 times 10 to the negative fifth, which gets me 1.14 molarity of my acetate ions. Okay? Which, if I wanted now to do it in sodium acetate as my solid that I'm adding, would mean 0.14 molarity of sodium acetate, just like we did calculated with the Henderson-Hasselbalch equation. So there's two different ways you can work this problem: Henderson-Hasselbalch or the procedure I've been showing you, which in my opinion, it seems a lot easier to do it as the calculation straightforward. One unknown, one equation, solve for it. But either way is fine, as long as you do it correctly. Homework 37. Okay, as questions about buffers and calculating the buffer. Once again, as I told you, I think you got to calculate the mass of it. So it's just a case of taking molarity, dividing by your molar mass, multiplying by your molar mass to get your nanograms.